Welcome to The Explainer. Today, we're diving into a connection that might sound a little strange at first, the salt in our oceans and the very air we breathe. But it turns out ocean salinity plays this huge active role in controlling atmospheric carbon dioxide, and really, we're just now beginning to understand how deep that connection goes.
You know, for most of modern science, researchers really treated the ocean's carbon cycle and its salt content as two completely different things. They were seen as independent systems. One was all about biology and chemistry, and the other, salt, was just kind of seen as a way to trace where ocean currents were going. But we now know that's just not right. The reality is, they're a tightly coupled system. Salinity isn't some passive passenger just along for the ride in the ocean's currents. Nope. It's actually a key driver, the master variable, you could say, that actively controls how much carbon the ocean can absorb and, crucially, how much it can store away.
This connection is so powerful and so fundamental that scientists have given it a really cool name, the salinity gate. Think of it as a whole new framework for understanding the ocean's role in our climate, one that finally links salt and CO2 together in a way we've never really appreciated until now.
And this is a really, really big deal. Why? Because this salinity gate regulates the single largest active carbon reservoir on our planet. The deep ocean holds an incredible 50 times more carbon than our entire atmosphere. So even a tiny change in how this gate works can have absolutely massive consequences for our climate.
So, the big question is, how does this gate actually work? Well, it operates through four key pillars, four mechanisms that explain exactly how salinity governs the ocean's ability to soak up and store carbon.
Okay, so here they are: circulation, solubility, biology, and storage. Together, these four pillars show us how salt basically acts as the master switch for the entire planet's carbon cycle. Let's break each one down.
First up is circulation. This one is pretty straightforward physics, actually. The saltier water is, the denser it is. And that extra density is what makes water sink in the polar regions, which in turn powers this massive global current we call the ocean conveyor belt.
And what's wild is how sensitive this system is. Just a small increase in salinity can actually speed up that global conveyor belt, what scientists call the meridional overturning circulation, or MOC, by a whopping 20 to 50%. That directly changes how fast CO2 gets pulled from the surface down into the deep ocean.
So the second pillar is solubility. You see, salinity doesn't just move water around, it fundamentally changes its chemistry. And it's pretty simple. Saltier water can physically dissolve and just plain hold more CO2 from the atmosphere. And we know this isn't just some lab experiment. If you look back at past ice ages, the oceans were a lot saltier. And scientists now think this effect, this enhanced solubility, was responsible for pulling an extra 30 to 50 parts per million of CO2 straight out of the atmosphere, which helped to cool the whole planet.
All right, pillar number 3 is biology. The ocean is just teeming with life, right? Well, salinity affects that life. It controls the structure of the water, how it's layered, and that layering determines the flow of nutrients up to the phytoplankton at the surface. This has a direct impact on what's called the biological pump, which is just how marine life captures carbon and sends it sinking down to the deep sea.
And the effect here is pretty staggering. A really tiny shift in salinity, we're talking as little as 0.3 practical salinity units, can change the amount of carbon that gets exported by this biological pump by 20 to 40% in some of the most important parts of the ocean.
And that brings us to our final pillar, long-term storage. I mean, it's one thing to get carbon down into the deep ocean, but it's another thing to keep it there. Salinity controls the ocean's ventilation, basically how fast that deep water makes its way back to the surface. And that's the deciding factor in whether carbon is locked away for thousands of years or just a couple hundred.
And the stakes are huge. We're talking about the fate of this massive reservoir of 38,000 gigatons of carbon. Salinity really is the gatekeeper for our planet's biggest carbon vault. It determines how much stays locked away and for how long.
And here's the really worrying part. We are already seeing this play out in the real world. As melting ice sheets dump fresh water into the ocean, especially down around Antarctica, the whole process is getting weaker. This freshening is slowing down the formation of that deep, dense water, and it's already cut the Southern Ocean's ability to soak up carbon by an estimated 10 to 20%.
So when you put all this together, realizing that there's this unified salt carbon system, it really changes how we have to think about our climate. The implications are profound,
affecting how we see our planet's past and how we predict its future.
For starters, our climate models have got to be updated to include this stuff. This new view also helps us finally make sense of those dramatic climate swings during the ice ages. But it's also a serious warning. If ice melt continues, it could weaken the ocean's carbon sink, creating a dangerous feedback loop that actually accelerates warming. And it even opens the door to some new and very, very risky ideas about geoengineering.
What this all boils down to is a major shift in how we see things. We just can't think of the deep ocean as some simple passive storage tank for carbon dioxide anymore.
Instead, we have to see the ocean for what it truly is, an active, dynamic system. It's a salinity-gated regulator that actively shapes Earth's carbon cycle and, by extension, our climate. You could say salinity is the hand on the thermostat. And so this leaves us with a critical and honestly a pretty unsettling question for our time. As we continue to pour absolutely unprecedented amounts of fresh water from melting ice into our oceans, are we, without meaning to, closing the gate on our planet's single greatest ally in the fight against climate change?